So far, we've looked at vaporization from kind of an energetic side and kind of an intermolecular force side, and all of that's going to come together in what we talk about in this video. So, what we are looking at is if you imagine an insulated container, it has an open top, there's some liquid in it, and those molecules, the ones that are at the surface, have the ability potentially to escape and become a gas. So, one question is what happens to the temperature of the liquid as the molecules vaporize? So, to kind of put everything that we have talked about together in one place, right? You're imagining molecules in the liquid at the surface. For a given temperature, those molecules all have an average kinetic energy. Some of them have a high enough kinetic energy that they can escape the surface and turn into a gas. As the molecules that have a higher kinetic energy escape the surface, the molecules that are still in the liquid form, the average gets lower. Right? If you have an average, a spread of kinetic energy values, and only the ones at the top are leaving, now when you look at the new sample and take the average of what's left, the average is lower. So the temperature will go down because the average kinetic energy is going down. We can also think about this using the fact that vaporization is an endothermic process. We have to put in energy to break these intermolecular forces. And so that energy is coming from the thermal energy of the sample. Now, the opposite is true. Condensation is exothermic. So if we take a gas and condense it into a liquid, all of those intermolecular forces, those interactions as they're forming, give off energy. So enthalpy of vaporization, this value has come up before. This is the heat required to vaporize 1 mole of liquid to gas. And we have the values for 100 degrees. So this is if you are at the boiling temperature of water. You would have to put in 40.7 kilojoules per mole to get the liquid to turn into a gas, or if it's a gas turning into a liquid, you would get out negative 40.7 kilojoules per mole. And this value does depend on temperature, right? If you are at a high temperature already, the molecules are ready to vaporize. If you're at a lower temperature, you will have to put in a little more energy. So at 25 degrees Celsius, it takes 44 kilojoules per mole to go from a liquid to a gas for water. This sets us up to do heat transfer questions that have more going on than just this thing is hot, this thing is cold, put them together and see what the final temperature is. We're going to do an example with this. And the question that we're looking at has 0.48 grams of water condensing on the surface of a block of aluminum. So gas turning into a liquid, that's condensation. That's exothermic. So that heat that is the result of the intermolecular force interaction formation will go into the block. So the rest of the question, if the heat released during condensation goes only toward heating the metal, what is the final temperature of the block? So we have water at 100 degrees, it's a gas, it's going to condense, and that amount of heat would be absorbed by the block. So we're not even going to, for this problem, take into account that once it condenses, we still have 100-degree water next to the block. That would be a second step. We could include it. We aren't in this problem. We're just going to look at this amount of water condensed, it was at this temperature, that amount of heat that is given off. How does it change the temperature of this block? So for the block, the heat absorbed is related to mass, specific heat capacity, and delta T. So any kind of heat transfer that has a temperature change, we can still use this equation. Now, where the heat is coming from is from the water. So all of the water that condenses is going to give off heat, and it will be absorbed by the block. We have the mass, the specific heat capacity, and the initial temperature of the block. So all we will have left to find is the final temperature in the delta T. My amount of heat given off during condensation, it's in kilojoules per mole, so I need to know my water amount in moles in order for this to work. So 0.48 grams of water, use the molar mass to convert that to moles, and then use the enthalpy of vaporization to convert that to just energy. Just this is the amount of heat that is given off, and that is negative 1.08 kilojoules. Now, all of that heat is absorbed by the metal. So the metal will have a positive 1.08 kilojoules. And our specific heat capacity is in units of joules per gram degree C. So I've rewritten this to be 1080 joules. Now I have everything except for the final temperature. So 1080 joules, and that is being absorbed by a 55 gram block that has a specific heat capacity of 0.903 and an initial temperature of 25. This would make my final temperature 46.7 degrees Celsius. Now, this is, like I said, this is just the very first step of this heat transfer. At this point, we would still have a block at 46.7 degrees Celsius and water at 100 degrees Celsius. There's a next step that I didn't calculate here that would give you the real and true final temperature of this block, which you're welcome to do and then ask about. I just don't have it here.